Sam, what the hectagon? You have the nerve to challenge me, the papa, to a little generalization war, to a battle rudesse, to some Yu-Gi-Oh duel. Okay, here we go. Here's going to be my video on generalizing something that has to do with the D. I'm going to punch you really hard today. I'm going to destroy you with the D and with Hakurumu Chaik Des. So yeah, watch Sam's videos. He has done something on Papa Fibonacci and generalizing the generating function. You can decide who's going to win up there, and more videos to come. And now I'm going to destroy you with the D. Have fun. Good morning, fellow mathematicians. Welcome back to another video. We are once again going to play around with the D, okay? This joke is getting old over time. Never mind. And today we actually want to find a solution to this nth order ordinary homogeneous differential equation with constant coefficients. And I did this up until the second order, okay? In a really formal way, and even for the first order in a really abstract way. And then I said, well, you can repeat this root finding process, blah, 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 up until nth order, okay? And I made videos on superposition that you can add homogeneous solutions together to get more general homogeneous solutions. Okay, this is a cool thing, but this time we really want to find the solution to this thing in a really formal way, okay? And we are going to use the D operator for this. And if you have watched my previous videos, you might know where this is going to go, okay? But we are going to go through everything step by step. And in the end, it was hopefully a nice ride for you, something really interesting for you that you haven't seen before. So at first, I want you guys to see that this thing right here is basically just a polynomial in our D operator, an nth degree polynomial at that. So if I were to rewrite this, we could also put it into this form right here. What we have is some kind of a summation running from, well, let's say k being between 0 and n right here. And what do we have here? Well, we have those constant coefficients, ak. Also, we have the D operator, D to the kth power in some way, okay, for example, to the nth power, to the first power, whatsoever. And also we have our y. And all of this is equal to 0. Now, this is kind of that form right here, okay? But all that's really missing is our e right here, our e term. And here comes an argumentation in I told you about in one of the last videos, okay? This thing is a polynomial, and the cool thing is if you know the roots of a polynomial, and this is where it's going to go, okay? We can actually turn this into the multiplication of its linear factors. And this is a really cool thing you can do right here. So what we can do, we can turn this thing into something completely equivalent. If we were to know all the roots of this nth degree polynomial in our D operator, we can also rewrite this as nothing but, okay, we have an nth degree polynomial, meaning we are going to have n roots. Starting from the first root, I'm going to put an I right here, to n. Then our root's going to be noted like this, D minus the ith root times y being equal to 0. It's just like with simple polynomials. When you factor x squared minus 1, you're going to get a linear combination as x minus 1 times x plus 1. It's as easy as it is, just with a d instead of an x, okay? And now if we were to write all of this out, what would we get? That's equivalent to saying we are going to have d minus, okay, lambda 1, and then d minus lambda 2, blah, 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 up until d minus lambda n, y being equal to 0. Now we are going to do something we have done before. We are going to give our y a new name, okay? Let y be equal to, and I'm going to put it like this. This y, right now, this renaming is going to correspond to the nth root. We are going to call it phi n, but also what we want to do, we want to equip this y right here with an exponential function, such that we can make use of this fact, d plus a. If we were to put e to the lambda n times t up here. We can make use of the shift property, okay, to actually bring this to the outside and eliminate our root. We have done this before. Take a look into the differential equation playlist. It's a really important part right here. We are going to multiply this thing with e to the lambda n times t. And this is going to work absolute wonders. Okay, what we are going to have now is, okay, this right here is going to be to n minus 1 this time, d minus lambda I, and then we also have d minus lambda n. I'm going to put it like this on purpose because we are going to be left with this in the end. And also our y is nothing but e to the lambda n times t phi n being equal to 0. Now, if we were to use our shift theorem, we are going to drag this to the front, but in each and every part of those linear factors, we have to add our lambda n to this, okay? Meaning that's equivalent to saying we have e to the lambda n times t. Also, we have our product of d minus lambda I and then plus lambda n. This is something extremely important. Don't forget this. We have to distribute it into each and every part right here, just like with here. And also we have d minus lambda n plus lambda n, resulting in d phi n being equal to 0. Okay, this has reduced quite nicely, and we are going to do one more iteration such that you can actually see the pattern. Overall, we are going to do n iterations, but in the next part you are going to see what this exponential function is going to be in the end after doing n iterations. Okay, bear with me right here. Now, we are going to rename this thing right here d phi n. What is this going to be? D phi n is going to be the thing that corresponds to the n minus 1th root. Okay, so we are going to call it phi n minus 1. Okay, some little index magic right here. And also, I hope the printer's not going to start. It's going to start. Give me a second. Hey, Vsauce, disturbed boy right here. Yeah, it was Professor Dr. Wilkins coming in here. He's one of the most badass guys I've ever met. He's such a monster, mathematical and physics-wise. Never mind. Okay, where did I end up? Okay, we had this phi corresponding to the n minus 1th root, but this time we want to get rid of the n minus 1th root. And also we want to get rid of lambda n, because this thing right here is kind of disturbing. It's kind of a new root. It's part of all those roots at the moment. Meaning we are going to equip an exponential function with lambda n minus 1, but also negative lambda n times t. Let me write everything out, and then you are going to see where this is going to go. We are going to have e to the lambda nt. We are going to have a product now ranging from 1 to n minus 2 this time. And then we are going to have d minus lambda I plus lambda n e to the lambda n minus 1 minus lambda n times t phi n minus 1 being equal to 0. That's a lot of writing right here. And now once again, exponential shift theorem. This is so magical right here. We're going to bring this to the front. And lo and behold, if we bring this to the front, we are going to have e to the lambda n times t times e to the negative lambda n times t. It's going to cancel out. What we are going to be left with after the second iteration is lambda n minus 1 times t with an exponential function around it. Okay, meaning we are going to be left with e to the lambda n minus 1 times t. This product, 1 being less or equal to I, less or equal to n minus 2. But also now we have to bring this argument up here into all of those. Meaning we are going to eliminate in the process the n minus 1 thing. We got rid of that already. Okay, also don't forget, if we, I totally forgot this factor right here. I'm terribly sorry. We also have this n minus 1 factor. We don't want to miss that. Okay. In here, I'm terribly sorry for that. We had d minus lambda n minus 1 plus lambda n. Okay. Using the exponential shift, we are going to get rid of this stuff. Okay, meaning up here we are going to be left with d phi n minus 1 being equal to 0. But what do we have in here? Well, we are going to have our d being preserved, but also we are going to get rid of this lambda n. And now what we have is negative lambda I, but also positive lambda n minus 1. I'm terribly sorry for this little for this little mistake right here. This was kind of confusing that the doctor came in, the doctor, professor, whatsoever. He's a professor, I'm pretty certain. So what can we see right here? Well, we see that after a certain iteration, this index on our phi is going to correspond to the root that we have on the outside right here. So if we were to do this process n times overall, we are going to be left with e to the lambda 1 times t times a product ranging from 1 to 1 of just d phi and, well, lambda 1 d phi 1 being equal to 0. Recursively, we are going to go all the way down right here. Okay, we are going to eliminate everything up until we are left with a certain phi right here. So after a lot of iterations, we are going to be left with e to the lambda 1 times t. But also, we are going to have d phi 1 being equal to 0. Now we can multiply both sides by this exponential function, meaning we are going to have d phi 1 is nothing but 0. And then on the next blackboard, we are going to talk about, well, of which form are actually our d phi case, for example, or our phi case in general. Give me a second, I'm going to erase everything and then we are going to be left with the grande finale. This last part is just so damn cool, seriously. When it all comes together, it's just, oh, it's just puts a smile on my face. It's so satisfying. Okay, you see, we have d phi 1 being equal to 0 after n iterations of doing this stuff up here. Well, if we differentiate something and it's 0, well, what was this original thing? Well, simply constant. Okay, that's the conclusion that we can have right here. So our phi 1, you can just simply integrate both sides, okay? Indefinite integration, it's 0 plus some constant c, okay? C, and that's, for example, element of the complex numbers. Never mind, really doesn't matter. Now, we have found out something really peculiar before. If we take a look at d phi n, this is nothing but e to the lambda n minus 1 minus lambda n times t times phi n minus 1, meaning we can go one step up. Okay, we are going to put everything in we have found out before. Now we are going to take a look at d phi 2. What does it look like? Well, by the exponential shift theorem and doing those substitutions, we are going to be left with e to the, well, lambda 1 minus lambda 2 times t. Phi n minus 1 is going to be phi 1, which is nothing but a constant right here. And here comes the really hard part. We have to integrate both sides, once again, with respect to t. If we were to integrate both sides with respect to t, well, integrating something that has been differentiated in the same variable is just going to result in this very argument right here, okay? Also, integrating an exponential function is really quite easy, meaning we are going to be left with, okay, phi 2 plus some arbitrary constant c. We don't need that, we can bring this to the other side because we are going to be left with a constant here too. Integrating the exponential function leaves us with this exponential function being preserved times 1 over this argument up here, times some arbitrary constant c. Lambda 1 and lambda 2, and also the addition and subtraction, are just constants. Meaning overall, if we divide a constant by a constant, it's going to result in yet another constant. We are going to call this thing C1, okay? And it's going to be preserved over time, okay? The same process is going to happen n times overall, leaving us with constant C1 e to the lambda 1 minus lambda 2 times t plus some new arbitrary constant C2. I'm going to call it C2. I'm going to do one more iteration, such that you can see a certain pattern right here, which is going to be so fantastic in the end. by this definition up here, yet again, and by what we had right here. What the hell is d phi free? Well, this is nothing but e to the lambda 2 minus lambda 3 times t times phi 2. But phi 2 is nothing but this right here, meaning we are going to be left with c1 e to the lambda 1 minus lambda 2 times t plus c2. Overall, c2, lambda 2 and negative lambda 2 is going to be eliminated, leaving us with c1 e to the, and I want you guys to notice lambda 1 is going to be preserved right here. Lambda 1 minus lambda 3 times t plus c2, and then e to the lambda 2 minus lambda 3 times t. Once again, we are going to integrate both sides such that we can get our phi 3. If we integrate both sides, we are going to be left with this thing. Once again, dividing those constants by other constants are going to result in yet other constants. We are going to keep their names as being c1 and c2, but also after integration, we are going to get yet another constant of integration. Going to call it c3. And I want you guys to notice a pattern. On our index of this constant, this lambda, this root, first root, is going to be preserved. On this constant, our lambda 2, our second root, is going to be preserved. Also, phi 3 is going to correspond to lambda 3 right here. Now, what does this tell us? Well, we can find an expression for our, I'm going to put it differently, for our cave phi right here. Meaning, this thing right here is just a sum running from, well, 1 to 3 in this case. Okay, that's 1 to k, thus 1 to k. I'm going to put the index I right here, yet again, and then this is nothing but ci e to the, okay, we are going to go through everything. Lambda 1, lambda 2, and I want you guys to notice this is nothing but e to the lambda 3 minus lambda 3 times t. Okay, we are going to go through everything, meaning this is lambda I minus lambda k, what we have right here. I want you guys to notice the pattern. This is really important, but that's the most satisfying thing ever. So this is just really cool in my opinion. Okay, and I came up with this on my own. That's the coolest thing. So this is something I find really cool. Now we have found an expression for our cave phi right here. So this is a general expression. You can probably prove this using the principle of mathematical induction, or an easier way to prove this is to take a look at a cave order differential equation and plug it in and check if it's really a solution to this differential equation. But we are not done yet, because this is just our phi. What we want to have is the solution y of t. How can we get back to that? Well, y is nothing but this right here. Y is just the nth phi times e to the lambda nt by our first definition. Meaning this is e to the lambda n times t. Then phi n. Phi n is by this definition nothing but our sum running from 1 to n of ci e to the lambda. Okay, and I forgot the t right here. I'm terribly sorry. Oh, this is so cool. Lambda I minus lambda n times t. If we were to multiply this exponential function by this one, lambda n and negative lambda n are going to cancel out in the process, leaving us with a sum running from 1 to n ci e to the lambda I times t. Et voila, my boys and girls. Isn't that bloody amazing? Okay, our fundamental solution to this homogeneous linear ordinary differential equation is of the form some constants times e to the roots times t, all the roots of this polynomial. This is what I proposed in earlier videos, but this time we have proven it to be correctly, and this is just so amazing. This is just so amazing. This is our solution, and it was so much fun. Calculating the stuff for this video, working with the D operator, it's just so much fun. It just puts a smile on my face. It makes me so happy. Papa is so happy. If you did enjoy this video, please like and subscribe, recommend channel if you like. If you want to support channel a bit more, buy those t-shirts I created, or support the channel on Patreon, or click on my skill share link, for example. This really helps support the channel. And up until the next video, have a definitely not sponsored by Hago Romo Chalk day. See ya.